When I travel with my geologists, I'm always slightly ashamed because they go out with a notebook,
Yes.
they go out with a compass and a hammer, and that's it. I go out with trunks and trunks of
samplers.
And they say, why do you need all that equipment? This is all we need and our brains. So I always feel a bit ashamed that I need all these crutches to work out what's going on with the hydrogeology.
So if Punjab just grew different crops other than paddy, that itself would have been helpful, right? Because just having all this water hang around and evaporate in rice fields.
Yeah, having so much water to evaporate is inevitably going to increase salinity. So choosing carefully what crops you put on at what time has a big impact on the groundwater, not just what you're abstracting to use it, but also what gets returned back to the aquifer.
Welcome to the Water Data Podcast, where we talk about the science, the stories, and the systems that shape our water future. I'm your host, Veena Srinivasan. Every couple of weeks, we'll chat about how better data and evidence can result in better decision-making and ultimately better outcomes for people and the planet. So if you're a student, a researcher, an innovator, a practitioner, or just curious about how we can better manage this precious resource, you've come to the right place. Let's get started. Welcome to the Water Data Podcast. Today, it's our privilege to welcome Alan MacDonald from the British Geological Survey. And Alan is an esteemed researcher and hydrogeologist, and he's worked both in India and Africa for many, many years. But today, we're really going to talk about Alan's work in South Asia primarily, and contrasting some of the work you've done both in the granitic aquifers of South India as well as the Indo-Gangetic Plain. Welcome to the Water Data Podcast, Alan.
Thank you. It's a real pleasure to be here with you.
Thank you. So I'm wondering whether we should start a little bit with history, because firstly, your journey is long and rich. And tell us a little bit about how you got started with work in India, and then we can kind of delve a little more.
Well, I'd spent a lot of my career working in Africa on the hydrogeology of crystalline basement rocks and looking at rural water supply. And I just completed quite a large project looking at how groundwater would respond to climate change in Africa and how rural water supplies would be affected by changing climate. And the people I was working with there, which was a UK Department of International Development, really wanted to do some similar work in India. Now, I knew a little bit about Indian hydrogeology and always found it fascinating, so I was really delighted with that opportunity. So what I did then was just to ring around some friends, email friends, people who knew hydrogeologists, particularly through the International Association of Hydrogeologists, to get together a team of hydrogeologists in India at that point to put together this project to look at how would climate change impact groundwater in the Indo-Gangetic Basin.
Right. And that was about in the early 2000s to mid 2000s.
Well,
that was when you started.
2010, 2011.
2010.
Yeah.
Okay. Yeah, because I remember that groundwater and climate change paper maybe was in 2011 or so.
Yeah,
so
that's
it was
right.
around that period. Okay.
Yeah.
But since then you've done a lot of work, and I think what really makes your work fascinating is you've done both kind of empirical measurement kind of work and then also the more modeling kind of work, which I think is always a very nice span of work that a person might do. So can you tell us about your early work on the Indo-Gangetic Plain and what were some of the findings, and then how you started looking at scale and typology and a lot of those. How did that come about? What did you learn from that work?
Yeah, sure. So I've always been a bit of a hydrogeological kleptomaniac. I like to take lots of techniques from different parts of hydrogeology to answer the question. So the question we were looking at here was, how would climate change impact on the Indo-Gangetic Basin aquifer? So it's a fascinating aquifer because probably it's the most prolific aquifer in the world. So you have maybe a fifth to a quarter of all groundwater abstraction happening from this aquifer. And it's in northern India and then flows into Bangladesh, but also in Pakistan as well. So it really is the floodplains of the Indus and the Ganges, and as the Brahmaputra comes in as well. So it's a flat area, but beneath the ground, it's very thick sediments of sands and gravels and clays. So one of the really interesting things about the aquifers formation is it's quite young. So as the Himalayas have grown up, then this basin in front of the Himalayas has got deeper and deeper, and it's filled with the sort of sands and sediments that have been eroded off the Himalayas. So it's kind of young aquifer, which makes the geology really interesting because you've got all these different sediments, be they sands and gravels or clays, and where you find water, it's dependent on that kind of geology. So that's, I suppose, where I started, Veena, was from looking at the kind of geological formation of that aquifer and trying to work out a bit about where you would drill, whether it be a lot of water or a little water, whether there was young sediments that might have arsenic in them, or whether it was older sediments that had been flushed through. So started with the geology.
So arsenic is not there in older sediments, is that correct? That where you have arsenic, it's almost always younger sediments?
Well, generally it's the younger sediments because they still have got the organic matter
which
in it
mobilizes
there, which mobilizes the arsenic out. So this kind of large sedimentary aquifer is quite variable. Although in hydrogeological maps it might be coloured one colour, probably blue, but actually when you delve into it in detail, there's a lot of complexity.
I mean, I think the one thing that emerges from your study at a very high level is don't treat it as one monolith, but it's very, very variable. And so what you do in different places has got to be different. So let's start with the western side of the aquifer, which is the overexploited, drier side of it. And I know you've done both on the Pakistan side of it as well as the northwest, western parts of India. So can you tell us a little bit about what's going on there? Because there's both depletion we've seen from GRACE and so on, and we know this, but tell us about the combination of their salinity as well. So can you just describe, what your studies have shown there?
Yeah, sure. So that kind of western part of the Indo-Gangetic Basin is the one that often gets the highlights. There was a very famous paper by MacDonald, and of course there's Tiwari in India as well, that showed with the GRACE satellites this great depletion. But actually that hides a lot of nuance and interesting hydrogeology when you look at it in more detail. So the way the aquifer works there is that you have quite a lot of rainfall in the northern part of it, so it's quite a lot of recharge in that aquifer, which is why it was quite prolific. But you've also had the canal network, and the Indo-Gangetic Basin has been hugely modified by humans over the last 150 years plus. So by creating the canal network, that water, some of the water from the canals, has leaked into that aquifer and made the water levels in the aquifer rise. So they're actually quite shallow in that part of the aquifer. So historically, maybe 200 years ago, some of the water levels might have been quite deep. But humans have, by putting canals in there, raised the water levels quite high. And it's on the back of that then the depletion has happened. So the modern depletion there should be seen in a kind of context of rising groundwater levels over the last maybe 150, 200 years.
I mean, that's really fascinating because that's not I have seen this in your papers, but it's not a story that makes the headlines, right?
No.
Because the story that makes the headlines is the Rodell et al.'s GRACE, big red dot in west. So let's just unpack that a little bit, because the canals came into this area during the colonial period, right? Starting in the late 1800s. What were the groundwater levels, or what would have been the groundwater levels at that time?
Well, in the sort of drier areas, so if you think of southern Punjab and in Pakistan, the southern Punjab, then the water levels might have been 50 meters deep in some areas. So there's in the 1960s, different scientists tried to piece together the historical groundwater levels, and one of the fascinating things I found during my early studies here in 2011 and 12 was there were some old files with 150-year-old groundwater level variations in it. So, it's one of these classic things where you find a book and you go, oh my goodness, look at that data. So that's why we managed to get funding for a second project to go in and do the hard work of just finding all these old records and kind of piecing together the kind of colonial groundwater level variations.
It's such a inspiration for students who do not think of their job as going and mucking around the basement of a Survey of India office or archives, somewhere and reading some of those, because they don't. Some of these are in colonial archives or they're in these gazetteers and stuff like that. So, what did you find from that poking around basements?
Well, basically, I've made a career of finding old bits of paper, really, and because there's so much useful information out there. So we're here, what we really found was that there was quite a lot of boreholes that had been drilled when the canals were put in the 1800s, and the groundwater levels at that point actually varied. There were some shallow ones, there were some really deep ones. So what we did was we digitized all the data, we pieced it all together, and then we created typologies. We said, well, here's ones that have risen steadily for 100 years and then have started going down. Here's ones that have risen steadily and then have continued high. And then we tried to look into the reasons for that. And the reasons were this interesting interplay between the canals, the groundwater abstraction, the river flows, but also very much the climate. So getting back to where we started, actually climate has had a big impact on groundwater levels across the basin. So when you've had...
Because of accelerated melting of glaciers or increased rainfall recharge?
Because of both. So we can see in our data that actually the rainfall that arrives on the plains themselves is very important. So for many places, that's paramount. It's actually the amount of rainfall that happens in the monsoon that defines the recharge. And then you've got the canal leakage. And then you've got what happens with the glaciers, because the glacier melt comes down, then feeds into the canals.
So let me just unpack that for a bit, because a lot of these places I would not have guessed, because rainfall is about 300 to 500 mm in much of those places that you're talking about, northwest Rajasthan, Punjab, and so on. But why is it that makes such a big difference? Is it just because of the alluvial nature, or the fact that it's mostly desert and there's not much vegetative use and therefore a lot more recharges?
Well, you're right. It depends very much on that rainfall gradient. So once you get down to Rajasthan, the rainfall isn't as important. But as you go further north, then rainfall does become much more important. You can get rainfall maybe 500 millimeters, which then is causing more recharge, and it's, of course, quite widespread.
Right. But it's rainfall essentially falling on like gravelly kind of stuff, so it's very high recharge rates.
It's very high permeability.
It's very high permeability.
Of the sands and gravel, so
and
you get a lot of
not
infiltration.
much of vegetative demand for some reason, because it's dry.
Well, of course, you've got all the agriculture now, so that's where the
modern
evaporation is coming from. Yeah. So looking at that part of the basin, we really need to understand what's happening to the canals, what's happening to the rainfall, and what's happening to the river flow. And depletion is a massive problem. So although I'm talking about this accumulation over the last 150 years, modern depletion, as we know, is a massive problem. But it's not universal. I think that's the key. There are areas, southern Punjab, that are suffering from flooding, high salinity in the groundwater, and that needs to be managed as well as the depletion that's happening further north. So you have these things right beside each other: depletion and flooding happening close to each other. And the way we understand that is by looking at canals, rainfall, and abstraction.
So that's really fascinating. Can we go kind of one step deeper to kind of unpack how... I know that you've done a bunch of tracer studies, firstly to show how modern and what's the ratio of modern groundwater to fossil water. Yeah. But how did you arrive at the mix of how much was glacier water, how much was rainfall, and then how much was fossil groundwater, and then how much was sort of modern recharge over the last 50, 60 years? How do you arrive at that?
Well, first of all, it's not easy. We're all looking for that one tracer for groundwater that might tell you where it's come from and how old it is. But generally, there isn't one tracer that tells you that. What we do is we look at a variety of different kind of signatures in the water. So one of them is stable isotopes. Another one is dissolved gases in the water. And the other might be the chemistry. Some of the traditional chemistry, like your chloride or sulfate, but also more modern chemistry, organic chemistry, whether there's caffeine in the water or whether there's pharmaceuticals in the water. So we use these different sorts of tracers to then try and back calculate where that water that you're pumping out your borehole, where it's actually originally come from and what residence time it is, how old it is.
That's very cool. Actually, I didn't think about, because you could almost look at when a particular antibiotic or whatever was introduced. And then if you, of course, these are very, very trace amounts, but I know that you have abilities to detect. So let's start with the stable isotopes, which is deuterium and oxygen-18, essentially. And for listeners who are unfamiliar with isotope hydrogeochemistry, I was wondering whether you can explain how you use stable isotopes, and then we'll go on to the others.
So what we use is the stable isotopes of water. So we know that water is hydrogen and oxygen. And in the oceans, if we think of a great reservoir of water, then we have weights. Oxygen has a weight, and hydrogen has a weight or a mass. And a very, very small proportion of that will have a slightly different mass. So they've got more neutrons. So and that's what we call stable isotopes. So it's a small proportion.
Typical oxygen has 16.
Yeah.
It has an atomic weight of 16.
Yeah.
And the heavier isotope is 18.
Yeah.
And essentially, if something has been just hanging around for a long time, the heavier isotopes stay back, right? Because the lighter ones preferentially evaporate.
Yeah.
Okay, I'm just explaining it so that...
Yeah, sure. So in the sea, then we kind of know what the different ratios are between these heavier isotopes, stable isotopes, so that these ones aren't sort of radioactive.
Right.
They're stable. So we know what the ratio is. But once that evaporates, then it all begins to change. So you're right. Once that evaporates and is in the atmosphere, then we have slightly different variations of the heavier ones and the lighter ones, because of their slightly different masses, they behave slightly differently.
Right.
So that kind of behavior then allows us to unpack that a little bit. So for example, the rainfall falling on the top of the Himalayas will have a different stable isotope ratio than that's arriving on the Indo-Gangetic Basin, because they're at different altitudes. So it's that difference allows us to maybe be able to fingerprint a little bit. Did this water originate on the top of the Himalayas?
Right.
Or did it originate as rainfall?
Because orographically, as well, as the front goes up, the heavier ones precipitate first,
That's right. Because they're heavier, they fall out first.
Okay.
But you can also get that with different types of precipitation. So if you get a very light rain, you might have a different isotopic signature from a very heavy rainfall event. So you can, so even in one location, so in Punjab, you'll have a variation in stable isotopes throughout the year that you can begin to map out. So that's where stable isotopes come in, and I've used them in different parts of the world. In Iceland, we were able to distinguish what was glacier melt versus groundwater, and in India, we've been using it to unpack how much has come from the rivers, which have originated in the Himalayas, and how much has come from rainfall falling on the Punjab. So that's been a really useful technique then to see how far the Himalayan water has penetrated into the aquifer.
Fantastic. And then how much comes from canals. But are you also able to then say the difference between modern canal recharge, which is maybe, in the last few years, versus what happened over the last 100 years? Is that also different?
Yeah, so there's some other tracers we can use to look at modern water. And that tends to be dissolved gases. Mm-hmm. So humans have been using things like CFCs and SF6, and they're really well mixed in our global atmosphere. But CFCs, you might know, they've been banned at different times because of what they did to the ozone layer.
Right.
So every few years, a different CFC was introduced. So you've got this kind of cocktail of CFCs in the atmosphere that's changed from about 1950 to the modern day. So when that rainfall, if it fell in 1960, that cocktail that's in the atmosphere at that point gets locked in to that groundwater. Once it goes under the ground and through the unsaturated zone, it gets locked in. So if we're really careful when we sample, so you've got to sample very carefully to make sure that the water coming out doesn't have a chance to have any contact with the air. Yeah. If you're really careful with that sampling, then you can preserve that original cocktail of gases. So
it's
that's
like
been
little
really good.
time capsules, isn't it?
Yeah.
Because you're able to do that. Yeah.
So it's a really useful technique, and there's only a few places in the world that are able to analyse for these sort of gases at the concentrations that we need for the groundwater tracing. So that's been quite helpful for unpacking this very modern recharge, so in the last 50 to 100 years, versus recharge that might have happened a few thousand years ago.
Right. So that's how you kind of reached. So by looking at the combination of these archival records, which is going into dusty, very old style work of going into dusty basements, and then very, very modern, high tech kind of approaches of looking at this, you were able to basically say that in different parts of Northwest India, the recharge came from different sources at different times. But more importantly, at the high level message, groundwater increased over the last 100 years, 150 years, and then started decreasing. When was the highest? In the 1960s would have been the highest?
Probably about 16th to 1980s. So
depending on when groundwater extraction took off.
Yeah, so groundwater levels were kind of as high as, and then some of them stabilized a little bit because maybe rainfall was a little bit higher and abstraction was beginning to take off. But you really see the decline since 2000. So that's when you begin to see the sharp declines in groundwater levels as people have been pumping out more and more groundwater. So and that kind of fall in groundwater levels at the moment is very much defined by the local groundwater abstraction.
Right, and that's coming a lot. The modern calculations are also coming from satellite data. And the GRACE satellite that we talked about earlier. So do you want to talk about what satellite-based measurements and how that's changed the game?
So the GRACE satellites have been a really excellent addition to the hydrogeologist sort of toolkit that we have. But we've got to understand what they are. They give measurements over a really large area. So the footprint of the measurement of GRACE is 400 by 400 kilometres. So it's not going to tell you what's happening
in your village.
In your village, or even your catchment. It's much, much larger areas. So to interpret it, then there's been so much work done by the labs, JPL and the rest of them, to give data to us that has already been modelled for corrections in the atmosphere and such like. So what the GRACE satellites tell us is changes in the gravity field on a month-by-month basis. So the Earth's gravity changes ever so slightly, and the only thing really that affects gravity at that scale is the hydrological cycle. That's the only mass that moves quick enough around the world.
How come they don't see things like cities or deforestation, or if you've wiped out an entire Amazon forest at 400 square kilometers, would that show up in GRACE as a signal at all?
It's not the same magnitude as the hydrology that we've got. I mean, you can tell some other things about the gravity field other than water. And originally, it was also used very much just to map out what our gravity field is at a kind of average gravity field. They do what we call a geoid. So these GRACE data have been really useful at saying what's happened at this large scale to hydrology, and they're almost like an independent check to say, okay, mass in this area has increased or decreased. So that's what showed in northern India, mass was decreasing. It's also been really useful for looking at glaciers around the world, in Antarctic or Greenland, and it's shown for hydrogeology. It's also shown that in the Sahel in Africa, groundwater levels have actually risen over the last 30 years, due again to land use change mainly. So that's GRACE, but there's also other satellite data. First of all, for rainfall. So the way that satellites now help us measure rainfall has been really helpful. Also interpreting for evapotranspiration to show how much different crops are pumping out groundwater.
Right. Because the difference between rainfall and evapotranspiration gives you your change in groundwater storage as well, right? It's another way to...
It's another way to look at it, and you can input them into your models. There's also satellites that can tell you a little bit about soil moisture. It doesn't penetrate very deep, but it'll tell you a little bit about soil moisture change. And then people were using InSAR. So that's radar that shows the level of the actual ground, so that if you pump out a lot of groundwater, then the land surface declines slightly. You can see that most clearly in California, where there's this amazing picture. I mean, you can look it up online, isn't it?
I have, because I took basic hydrogeology first in California.
Yeah, so you'll know that wonderful picture.
I have seen that with there's a big pole, and then you can see where the land used to be. And
and it's pumping out of groundwater that's squeezed.
How come you don't see that in the Indo-Gangetic Plain or the Punjab area as much? I mean, you don't hear about it, or how come it's so much smaller? Because it's all unconsolidated sediment that you're pumping the heck out of.
So I think there's still a bit more work to be done to map it out across the Indo-Gangetic Basin.
Is it because there's less clay, for example?
But yeah, it's to do with the sediment. So not all sediments compress the same. So if you've got clays, then you can squeeze them, so they compress. But if you've got a kind of sand or gravel,
they hold up better.
They hold up much better. They're not as compressible. So these satellite data are really great for giving us more information, not just about what's happening to groundwater, but the driving data, like the rainfall and such like, that's affecting groundwater as well.
So before we drift east to understand kind of the Ganges water machine and all of that, what's happening in the salinity zones? I mean, how come, when you said there are places where you have depletion right next to places where groundwater has risen so much it's waterlogging? And how come, you think about these aquifers as being so well connected? How is it that equilibrium or difference persists for over long periods of time? Why doesn't it just all equilibrate faster than?
So when you start pumping an aquifer, you can think originally an aquifer groundwater flow is often 2 or 3 dimensional. It's flowing. It's recharging, it's flowing, it's discharging from springs or into a river as base flow. But once you start pumping, then actually the flow gets disrupted and much of our fluxes become vertical. Your water's coming in and then it's been pumped out. So our cells actually become a bit smaller because you've got the recharge and the abstraction. So that's why you can get things coexisting near to each other, because flows are less lateral and more vertical. And
also you're continuously pumping on one hand and you're continuously recharging on the other hand. So those equilibria are sort of maintained.
Yeah, at a kind of local level. So what's happening with the salinity is, again, it's as in everything in hydrogeology, it's really complicated. There's lots of different mechanisms that make groundwater saline. But basically, if you've got a lot of water near the surface, then you get a lot of evaporation, and it evaporates off as a kind of distilled water, and it leaves the salts behind. So you get this salt accumulating in either the soil or in the groundwater, and irrigation might wash that back down again. So you get this kind of increase of salinity. And once you start using that groundwater for irrigation, then that can accelerate, because then you're using slightly salty water, so you've got more salty water going back into the system.
How much of those salts are geogenic versus anthropogenic in nature in these regions? Is it just that the Himalayan sediments are saltier than others, or is it just that they're putting crazy amounts of agricultural chemicals?
So that's a really great question, and it's one we're looking at my current research project is trying to work out that kind of salt balance across the Indus Basin. So we're trying to work out, is the hydrological cycle and the salt cycle, are they in sync or are they out of sync? So in other words, is there a lot of geogenic salt in the aquifer that's come down in the past that's been dissolved out. So actually a lot of it, because the aquifer is quite modern, it's only been developed since the Himalayas have been put in
modern
place.
By geologist standards. Let's be clear about
That's
this.
True. Yeah, it's not hundreds of millions of years old.
It's only tens of millions of years old.
So it's very young. So a lot of the salinity that we're seeing at the moment is due to these kind of shallow groundwater levels. You also haven't had what we call a marine transgression across the basin. So when we first started looking at it, I thought, well, with the salinity, particularly when you go down the bottom of the Indus into the Sindh, I thought surely the sea must have come across here. But actually, I don't think there's been a marine transgression at all. So it is all salt that's originated from on land. So it is what's happened from sediment that's been eroded from the Himalayas. Some of that gets dissolved in the water. So if you measure the salinity of the river water, it might be 100 milligrams or so per litre of salt in it. So if you have that water, use that to irrigate, then
it gets concentrated.
It begins to get accumulated. And in the past, and even now, people have dealt with that by trying to flush that out of the soil into the groundwater so that the soil remains less salty, and that's increased the salinity.
So
in
if
the aquifers.
Punjab just grew different crops other than paddy, that itself would help, and did it with drip irrigation and so on, that itself would have been helpful, right? Because just having all this water hang around and evaporate in rice fields year after year.
Yeah, having so much water to evaporate is inevitably going to increase salinity. So choosing carefully what crops you put on at what time has a big impact on the groundwater, not just what you're abstracting to use it, but also what gets returned back to the aquifer.
If you find this episode to be valuable, please like the video and check out more episodes of the show. And don't forget to subscribe to the Well Labs YouTube channel. And if you think someone else, maybe a colleague, a student, a friend, or a fellow water enthusiast, might find this show useful, do share it with them. We hope to reach many more change makers like you. No, that's fantastic. Shall we start drifting east now? Because the eastern Indo-Gangetic Plain looks very different, of course, from the northwestern. So maybe we can start talking about that and the Ganges water machine, because you don't see the bright red spots in eastern Gangetic Plain. So maybe we can start with this. Is it just because we've developed it less, or is it because it's getting all of that subsurface recharge flowing in from the upstream areas? And which of those is kind of more important? And therefore, then it becomes the question of, can Eastern India ever become like Punjab, or is it going to be, always going to be different? And I think and then you can maybe explain the Ganges water machine as well.
Yeah, sure. Well, as you move eastward down the Ganges, then you have lots of changes going on. One of them is with the sediment itself. So as you get further away, I suppose, from the Himalayas, then you have finer material in the aquifer. So things like silts and clays, because the heavier sediments drop out first, and then so you get more sort of clay rich. So you get maybe more layering. So you get more clay layers within the aquifer, and you get more depth stratification going on. So that's what happens a little bit in the aquifer. But you also have this huge rainfall gradient. So as you drift east, you get so much more rainfall. Right.
You're going from like about 400 to almost 1,200 in like Bihar, and then of course even higher when you're talking about the Brahmaputra.
Exactly. But even if you think in Punjab, you also have a gradient that goes north-south.
Right.
So in Punjab, you might have 1,000 millimeters as you're closer to the Himalayas, down to 400 in the south. So you have this gradient both ways. But generally, as we're going eastward, the rainfall increases massively into the aquifer. So you have these two kind of gradients going on. And how that affects the hydrogeology then is you get so much more recharge. So if we go right the way down to Bangladesh, there's probably as much groundwater abstraction happening. You get very high spots of groundwater abstraction in Bangladesh as you do in Punjab, but you don't see as much of depletion regionally. You get some local depletion. And that's because the amount of recharge that is actually happening.
And that's rainfall recharge, not just subsurface transfer.
So, so it's it's a really good question, and one that a lot of hydrogeologists have been trying to unpack, particularly down the bottom of the basin in Bangladesh and in West Bengal, is how much of that water has come from the sides in and how much has come
from the top
vertically down. So I think if you think, first of all, the shallow aquifer, though, if you think of maybe 50 to 100 meters deep, a lot of that recharge is happening from rainfall locally and is also happening from rivers. And if you move slightly further up the basin from canals where they are, like in Bihar, there's quite a lot from canals. But most of it is happening from rainfall. So we had a lovely study in the River Gandak, where we again used our isotopic techniques and our modern tracing techniques to try and work out how much of the water was from the river and the canals and how much was from rainfall. And that uncovered there that a lot of what was going on was rainfall recharge at that point, rather than canals, which in southern Punjab, most of it canals, but in Bihar and River Gandak, it was mostly from rainfall. So that's what's happening there, this massive amount of rainfall recharge.
And so that's allowing, and that's just because the rainfall is higher. And again, we're still talking about sedimentary aquifers, so there's still a lot high rates of recharge as well. And then also you have these huge flood episodes also, because it's also a lot of water that hangs around for a long period of time, right? It's not into the floodplains and so on. It's not just staying in the stream and going into the...
Yeah, so you've got this more widespread flooding, which, if there's space in the aquifer, can then infiltrate into the aquifer. And this is where we get onto the Ganges water machine, I suppose, because that process that people see, which is we've got a lot of this surface water there, it can infiltrate into the aquifer. But if the aquifer's full, it doesn't infiltrate into the aquifer and just carries on causing problems and flowing downhill. So in the 1970s, people began to think about this, what they called the Ganges water machine. Well, what if we can abstract a lot of that groundwater out
in
during
the dry
season, so lower groundwater levels make space for that water, then that water can infiltrate. So it's an elegant idea in theory. In practice, it's quite difficult, I think, to implement. But it's happening naturally, and there's been some great work that's showing that happening in that bottom end of the basin. So Shams and Richard and co published a paper a few years ago showing how they called it the Bengal water machine because down the bottom of the basin, showing that the pumping of groundwater in the lower end of the basin has increased groundwater recharge in that area by allowing space in there.
So has it both increased groundwater recharge as well as reduced flood peaks in any way? How does it work on the flood side of it?
I'm not sure on how much it's reduced flood peaks. I've not really.
Hydrogeologists don't look at surface water. Regarding surface water, we still are different.
You've uncovered a flaw in my in what I do, but I think the scale of it at the kind of the Ganges River scale is quite large to look at. So at a smaller scale, things like that can happen. At that large scale, I don't have the evidence to have looked into see what's done for flooding.
So let me ask you a different question, because the arsenic problem is all primarily in the eastern Indo-Gangetic plain, right? So the Bengal, Bihar, so on and so forth. And you said earlier that the more modern sediments have more arsenic in it. Why is it that you only have modern sediments in the eastern Gangetic plain then?
So I suppose the first thing to say is that arsenic mobility is quite complicated. There's a lot, as you and I know, there's lots of different processes that help mobilize arsenic into the water. But one of them is to do with the age of the sediments. So if you've got younger Holocene age sediments, then it tend to have more organic rich material in it, which then allows the arsenic to be more mobilized. So what hydrogeologists look out for is where are these Holocene deposits? Where are they? And mapping them out. And you're right, a lot of that's in the southern end of the basin. but also you actually get it in the Indus as well. So there's been some recent work that has then highlighted that you do get arsenic associated in the Indus Basin with these kind of modern Holocene deposits as well. Maybe not to the same extent.
I guess it's going two different directions coming from the same.
Yeah. So in the Indus, it's quite close to the river where these Holocene deposits are. So that's, I suppose, where the arsenic is in the eastern part of the basin. And when that was uncovered, then people began to look for where's there water that's got less arsenic in it. So the obvious place to look was deeper, where the sediments were a bit older. So there's been a lot of work by hydrogeologists, across India and Pakistan and Bangladesh, looking for deeper groundwater, and also trying to work out if you start pumping that deeper groundwater, which doesn't have so much arsenic in it, what then will happen to the system? Will that draw down the arsenic into the deeper aquifer, or not, or is it safe? And that comes back to the question that you asked me a little while ago. In that part of the basin, is the water coming vertically down, or is it coming from the sides? And that has real world implications for public health.
Right.
Yeah.
So, I mean, just in case there's anyone who doesn't understand the arsenic problem, the problem emerged when we first moved from surface water sources, which were considered unsafe, unprotected sources, to groundwater, because groundwater is considered a safe source. And of course, they were looking at that time in the 60s and 70s purely from a pathological bacterial risk point of view. And then they moved to groundwater and have a much bigger problem, which made me wonder, why didn't they move back to surface water and just, do, instead of doing groundwater treatment? But this is for another episode, maybe. One thing about arsenic is when I've not worked in that part of the world, but when you look at the papers, it sounds like even in a single village, you can see very, very different arsenic levels in different parts of the village. How come that you have that kind of variability even in such a small area? And is that correct, firstly?
So I should first say that I'm not a hydrochemist, but I've worked with some really good hydrochemists. My colleague Pauline Smedley has done a lot of work on arsenic in this part of the world. So it comes back to, again, what we said at the beginning: hydrogeology is complex, and geology varies considerably from even in a small area. Depending on whether you've got clays or whether you've got organic rich material. So you have these kind of differences. And that means the what we call the redox conditions of the water can change from place to place. I'm from Scotland, you might be able to hear from my accent. And a lot of our groundwater supplies in Scotland come from floodplains, but really small floodplains. They might be 100 metres wide, which is not very big compared to the Ganges. And in developing groundwater sources in Scotland, you'll find drilling 10 metres apart, you might get a water that's high. For us, it's not arsenic, it's manganese. Similar kind of process, redox conditions controlling that. And when we look at it in Scotland, it's all due to the old paleo channels. So you think of how an alluvial system is laid down. It's just rivers moving around, depositing channels, and that's what we've got at a much larger scale in the Ganges floodplain, and down to 10, 12 kilometres depth. You've got rivers that have moved around, depositing either clays, organic material, sands and gravels. So you have that complexity at a kind of local level.
So if you had an ancient clump of trees, that was going to make a difference to where you have arsenic today.
Yeah.
And that's why you can have variability even within a small area.
Because it's all laid down by these rivers.
Got it. Do you have our episodes running in the background? If you're curious about a technical term that we use or an acronym we've forgotten to expand, check out our video episodes on YouTube. We have on-screen explanations that might be useful. Can we move south now? Only because I'm so excited that we have you here that I want to kind of cover all of India.
Okay.
We do talk about things in other parts of the world, but kind of, most of what we cover is about how water data in this podcast is really how data and these insights kind of impact water resources management in India. So I've had the pleasure of working with you in Peninsular India on the crystalline basement aquifers. And it's very different, isn't it, from everything we've been talking about with rivers deposit. Okay. And it seems to me that this is even harder than those alluvial systems. So can we talk a little bit about what's happening in most of Peninsular India?
Yeah, sure, Veena. And crystalline basement rocks are very, very different to the kind of sediments that we get in the Indo-Gangetic Basin because it's hard rock, isn't it? It's getting water out of a stone. It's hard rock with very little or no porosity itself. So where is the groundwater in crystalline rocks? Finding water
in little
there.
Cracks and crevices.
Cracks and crevices, and in weathering as well. So the history of how that crystalline rock has been weathered, has been, the top surface has been changed into soil, how that's evolved over the last millions of years is very important for hydrogeology. So crystalline basement rocks, the hydrogeology, is even more complicated than the Indo-Gangetic Basin aquifers. So when talking about the hydrogeology here, farmers have been using that groundwater, been great at finding that groundwater and using it. But the hydrogeology here is determined by the lack of storage. So if you think of the Indo-Gangetic Basin as a massive reservoir, you've got the sands and gravels with all that water stored in between the grain sizes. When we go down to crystalline rocks, you don't have the storage because, as we say, it's just in little fractures that the water's there. So managing that storage and managing that through dry years is what can be really complicated.
And I think what's always fascinating, if anybody is listening to this, looking at it, you almost see these rivers in Peninsular India as being straight lines, right? Because the rock fissures and then the water finds its way, and so the rivers are really just on fissures. Is that right? On fractures.
Yeah. So it's a fracturing history of these different rocks that is important. And crystalline rocks, you also get different sorts of crystalline rocks. So the work that we were doing here together was trying also to see how the different ancient crystalline rocks, be it a sheared, a sheared gneiss, or be it a granite, be it an really old sediments that have been heated up and compressed and deformed. It's saying, well, does the hydrogeology change between these different old, twisted kind of crystalline rocks? So the way that these rocks' behaviour changes is also determined by the fracturing history, as you're saying. Where are the faults? Where are the fractures? Where are they been actually weathered? So we had some geologists working on it, and they of course loved it. They had their hammers out looking at the different sorts of rocks, and they were mapping fractures in lots of different quarries and such like to map out the different typologies of fractures you get in different crystalline rocks. And what we did find was that some crystalline rocks have higher permeabilities than others because they tend to fracture more easily than other ones. And some fracture more vertically, some fracture more horizontally. So again, you can begin by using hydrogeology tools, you can begin to unpack which areas are likely to be better for groundwater, which ones are likely to have more storage, even though the storage is all pretty low, and which are likely to have less storage. And we also used a lot of our hydrogeological tools here as well.
And tools, literally hammers. So if you want to talk about sophistication, it was fascinating for me to travel with the BGS team and see them, how they use like little hammers.
When I travel with my geologists, I'm always slightly ashamed because they go out with a notebook, they go out with a compass and a hammer, and that's it. I go out with trunks and trunks of
samplers.
And they say, why do you need all that equipment? This is all we need in our brains. So I always feel a bit ashamed that I need all these crutches to work out what's going on with the hydrogeology. But using the stable isotopes, they were quite helpful here to look at what was happening to the ponds and the tanks. 'Cause
Yeah.
that's another big part of the story down here.
Yeah.
Is how do the ponds and tanks recharge the groundwater? So we used our CFCs and SF6.
And the answer was not very much.
Well, yeah, regionally not very much.
Yeah.
They were important locally, for the boreholes just around the tanks and ponds, but actually regionally didn't have.
I think this is a general kind of important insight, because one thing I think that I've learned from everything that you've just said, but is that people forget that all of these rivers and tanks and so on are point or line interventions, whereas stuff that happens on floodplains and aerial stuff is just so much bigger.
Yeah.
That it's always going to just in terms of magnitude, it's going to be much higher than things that happen along little lines and dots.
I think you've got that just right, Veena. It's a question of scale, isn't it? And we might do our studies on this tank and say, oh gosh, it's had this great influence. But when you scale that up across a huge catchment,
it's 1% of the area.
Yeah, and a small change to rainfall that year, because it's integrated with the whole catchment, might have a much bigger impact regionally on what's happening to groundwater.
I mean, this is really, really important, because there's a lot of people that just forget how important rainfall is. And so we'll see a lot of people go out and do stuff, try to boost recharge rates, which is great. I mean, you should do it. But forgetting that rainfall is such a big signal that they'll say, oh, groundwater levels went up. I mean, and forgetting that it just rained a lot more this year.
Yeah. And I remember that when we were doing the study and with Shekhar Moody here, during the time we were working on the Barambadi with you, which was a great privilege. We were looking at the groundwater levels, and I think we had 10 years of groundwater levels, and they were going down. So we're going, it's depletion. And then during the study, there was a really heavy monsoon, and it recovered completely.
So this was, I don't know, this was a story of my PhD thesis in Chennai. I started in 2003. I started fieldwork in 2003, 2004, which was the biggest multi-year drought, and pipe supply shut down and everything. And if you looked at the 10-year record, it just looked, and the entire story and framing of my thesis was, this aquifers in this place have depleted, and it was this whole story. My entire thesis was based on that. And then 2005, it rained and flooded. It was the heaviest rainfall in 100 years, and everything preset to pre-development levels. Amazing. And so you forget. Then I didn't have a thesis, so then I had to go in a different direction. But of course, then the thing is, rainfall matters.
Yeah, and also the scale of our measurement matters, doesn't it? So that's why hydrogeologists are always looking for more data and longer data, and that's why I spend a lot of time rummaging around in basements of different offices trying to find old data, because even a few long-term groundwater level records can give you that broader picture of what's actually happening to recharge, not just in the last year, 5 years, 10 years, but over 20 years or 100 years.
Right. Yeah, as we were saying, for when you just realize how important it is, and that's why having these old studies. But I think an inspiration, I hope, that any young students starting off on their career will be to go and poke around some of the Central Groundwater Board offices and so on, where a lot of the early work in the 60s and 70s was done actually by British Geological Survey. And now when I go to some of these offices, or when I was a PhD student at least, and I went and sat in some of the libraries and just read kind of the early geological studies, it just gives you such a perspective, which I think is what you're saying is it's really necessary to take a longer view and not like a 2-year view of groundwater. Yeah,
absolutely. And in terms of data, but also in terms of studies, there were some amazing studies done by Indian hydrogeologists and others in the 60s and 70s, where maybe there was more luxury to spend a lot of time in the field, to spend 3 years studying one aquifer. So some really good reports there. And also groundwork conditions were a little bit different. So being able to read these reports and see what people did then. And also some techniques worked a little bit better in the past. If you think of one way that people dated groundwater is with tritium. Now tritium, there was a bomb peak from tritium in the 1950s and 60s.
And in India in early 70s.
So you had this massive peak, which then allowed tracers during the 80s and 90s from looking at that tritium, we're really, really good. Now, the signal just now is almost too low. It's really hard to interpret. But back then, the signal was really strong. So looking at these older studies actually is actually better because the tracer was stronger. So
because tritium has a half-life, it disintegrates
11 years, yeah.
after 11 years.
So it goes down quite quickly. So looking at these old studies and working out learning what the old people did in the past is really helpful. And then interpreting that in a modern context. We've got different tools now. We've got some slightly different understanding. So using your modern understanding to build on the work that people have done in the past, not just, as I say, their data, but also their understanding and their conceptualization of what was happening.
Yeah. I think I want to just zoom out to the global scale for a minute. I think of course, the project that we're working on together now involves looking at both India and Africa and sort of some cross-learnings and comparative work across those. And one immediate thing that strikes me is in India, we're really talking about overexploitation and cutting back. And Africa is, of course, still in the process of developing water resources. And so conversations can look very different. They're seeing like depletion in pockets, but for most part, it's a continent with abundant groundwater resources. And so my question is, if India had abundant groundwater resources just maybe 1 generation ago or 1.5 generations ago, and it's not taken very long to kind of reach this point of crisis. And I was wondering, is that even something which is part of a conversation with Africa, or is it just such a big continent without too many people that they can really afford to exploit for a long time without worrying too much about consequences?
So that's a question that is forefront in my mind and a lot of people's minds, because there are different approaches you can take to helping to develop groundwater in Africa. And I like to call it globally a tale of two groundwaters, because this kind of narrative that we have is very right for much of India of overexploitation. We need to manage these groundwater resources because taking out too much is having all these consequences. That kind of narrative has kind of taken over the whole world. And for some parts of the world, and particularly some parts of sub-Saharan Africa, they've not had that opportunity of mass groundwater exploitation. So which pathways should people follow? Should it be a very precautionary one and say, okay, we don't want to end up like India's groundwater resources, so we don't want to overexploit? But they might say, well, we would like to follow some of the economic pathway that India's happened.
Which happened because of groundwater exploitation,
exactly.
Right? So that's the
So you have this bit of a conundrum. So I think as a hydrogeologist, I think what we've got to do is help show the consequences of actions. So say, okay, if you pumped out lots of groundwater here, this is what might happen. But for many parts of the sort of African aquifers, they're not currently being overexploited.
Right.
So as you say, you've got different population densities. You've got much larger distances between people. Actually moving drilling rigs around can be quite complex. So there's a lot of aquifers where groundwater levels are not really being depleted. And as we said for the Sahel, for example, groundwater levels are rising in parts of the Sahel and much of the Sahel due to kind of land degradation and increased groundwater recharge. So there are opportunities there, and it's helping to guide the decision makers, whether it's the people with the money or whether it's politicians or it's local farmers. It's trying to help them see what's a future pathway. How can groundwater help, or will exploiting groundwater here hinder you in the long run because it will lock you into a way of working that might be destructive in the long term. So as hydrogeologists, we should be prophets, trying to work out what's actually happening in the future or telling people what might happen in the future, rather than being policemen saying you can't do this or you can't do that.
Right.
Just helping people understand
what we call building
a
better crystal ball is, one of the ways we've...
That's a good way of putting it.
Yeah. I have one question in the Indian context now, like the horse has left the barn and it's run away and we are in where we are. And now the question is, how do we bring it back into control? And you're not an economist, so I'm not going to ask you questions about, how pricing and so on. But there is still this question of how do you define a boundary unit within which you can manage, right? And so India has this big program called the Atal Jal Yojana, which is sort of a participatory groundwater management scheme. But the question has always come, what's kind of can you manage it at the village level? So if everybody in one village decided to get a Gram Panchayat, got together and said, we will not abstract more than this, in which types of aquifers, at what scale does that make sense? Because a lot of the US, for example, which also had a groundwater problem, California, for example, and then they passed the Sigma Act, a lot of it is based on having defined groundwater districts in some way. Does that have to be hydrogeological? Does it not matter? You can just say, fine, as long as every village does it, it's enough. How would you think about this from a hydrogeology point of view?
Well, I think you don't want to be a complete purist about this as a hydrogeologist, because the most important thing is that some sort of management happens. So if defining that boundary is going to help or hinder that, then I would just go with whatever boundary is going to help that management actually happen. And groundwater, we have our models and we show groundwater moving, but it doesn't move that quick, over a time scale. So if it's being done at a village level, if it's been done at a district level, then it is going to have an impact.
It's going to have an impact. So if everybody cuts back and you do it at a district level, it's still going to make
and we've got to,
perfect, but
got to remember who are the people that really manage groundwater? Well, they're the people who use it.
Yeah.
So for India, that's the farmers. That is our groundwater managers, really, because they're the ones who are pumping out the groundwater and using it. So it's empowering and encouraging people who are using the groundwater to be able to manage it in a way that helps them long term. That's really what we need to do.
But it can't be too small, because if 25 farmers got to do it and everybody around them is pumping the heck out of the groundwater, it's not going to help. But as long as it's a large enough unit for it to be effective, is what I'm hearing you say.
Yeah, so over tens of kilometres or something like that. You're right. If somebody just within
them and their neighbours,
500 by 500 metres is probably not going to make a huge difference. But over a few kilometres, then that can make a difference. But as hydrologists and hydrogeologists, it's our job to see how that connects up. So if they're doing that, but somebody's changing what's happening to a dam further upstream, that is going to affect groundwater resources if it's coming from the river and such like. So as hydrogeologists and hydrologists, then it's worrying about that bigger picture and how a whole catchment kind of fits together.
Fantastic. Alan, it's been a pleasure talking to you. I did wanted you to give us one last bit of inspiration, because India is a country where the bulk of public investment goes into surface water, but the 80%, the majority of actual use is groundwater. And we have significantly underinvested in groundwater as a profession and hydrogeology as a profession. So if you had a hope or words of advice for young people starting off their career, what would you tell them to kind of think about? What should they invest in? What should they be looking and thinking about?
Well, I suppose the first thing I would say is that there's not really a better career than hydrogeology. It's such an interesting thing to look at, groundwater. It's so variable. There's so much work to do. You can quite quickly become an expert in something, because it's so there's so many different sorts of aquifers. There's so many things to look at. So I would say just if you're interested in hydrogeology, if you like groundwater, then just keep exploring it. There's lots of different techniques we can use, and we're finding new techniques all the time to explore groundwater. But there's also the old techniques, looking at old reports, old data. There's lots of things to be found out there.
Old techniques in new places, along with new techniques.
That's a good way. Good way of looking at it. And I think as hydrogeologists, or as people who are looking at groundwater, it's one of the most important things to be looking at the moment. Water security long term. People are using more and more groundwater, and with climate change, more people turning towards groundwater. So we need people to be looking at groundwater, and we need people who are good technically, but also inspired by it.
Fantastic. Alan, thank you so much for chatting with us today. It's been an absolute pleasure because I feel like I got to explore all of India's groundwater in just one episode. So thank you very much. It's been a pleasure.
It's been my pleasure too. Thanks,
Thank
Veena.
you. That's it for this episode of the Water Data Podcast. Thank you for listening till the end. If you enjoyed this conversation, please subscribe to the Well Labs YouTube channel and share this episode with your friends and colleagues. You can find the Water Data Podcast on all major podcast platforms. Until then, stay curious and stay connected. Thank you.